when we are working with alternating series, it's important to keep in mind that the only test for convergence or divergence that we've gotten so far in earlier sections of this chapter, the only test that applies also to an alternating series is the divergence test. All the other tests, the integral test, the ratio test, the root test, all the other ones work for series of positive terms. So there are two things that we have to think about to use the alternating series test. Thing number one is that the terms must be non-increasing in magnitude. So if we take the absolute value of each term, they need to be non-increasing. And then the second part of this says that if the limit as k approaches infinity of the magnitude of the kth term, if that limit is equal to 0, then we can say that the series, if k starts at 1 and goes to infinity, of a sub k converges. So any alternating series, if the terms are decreasing and the limit of the kth term is 0, then we can conclude that that function or that series converges. Now, a good rule of thumb is when you're working with an alternating series, kind of work through these two parts of the test in reverse. Find the limit first, and if you get 0, then look and see if the terms are not increasing. So if we start with an example, maybe this one. Sum, if k starts at 0 and goes to infinity, of -1 to the k power over k squared plus 10. The first thing I'm going to suggest that you do is let's work the limit as k approaches infinity of 1 over k squared plus 10. Okay, you can see very quickly that that limit's going to go to 0. So because the limit of a sub k is 0, then let's look and think about some function f of x defined by 1 over x squared plus 2, x squared plus 1. Does it decrease? Or does it not increase? Well, one easy way to prove that something is decreasing is to find the derivative and show that that derivative is negative. So the derivative of this function ends up being negative 2k over, we were working with x, so it would be negative 2x over x squared plus 1 squared, which is going to be less than 0. So we've got non-increasing, and we've got terms go to 0. So we can conclude that this series converges. All right, let's look at another example. I've got the series, if k starts at 1, goes to infinity, of -1 to the k plus 1 power times k times the sine of 1 over k. If we start with the limit as k approaches infinity of k times sine 1 over k, Looking at it the way we have it here, we've got something in the form infinity times 0. Sine of 1 over k is getting closer and closer to 0 as k increases. So that's really not, that's an indeterminate form that's not very helpful. It's not one of the forms that L'Hopital's rule is going to apply to. So we fix it, or change it a little bit. Instead of multiplying by k, let's think about dividing by 1 over k. This gives us 0 over 0. So we can use L'Hopital's rule on this limit and look at a limit as k approaches infinity of the cosine of 1 over k times the derivative of 1 over k over the derivative of 1 over k. And simplifying that, the limit as k approaches infinity of the cosine of just 1 over k. And as k approaches infinity, the fraction goes to 0. Cosine of 0 is negative 1, which is very clearly not equal to 0. So actually what we've done here is we've shown that this series diverges by the divergence test. The divergence test says if you work the limit and you get something that is not equal to 0, the series is going to diverge. And that's what we've got right there. So we don't even have to bother with looking at whether or not the terms are going to be non-increasing. We already know just by looking at the limit the series is going to diverge.